Hi, welcome to Calculus 2. Today we are going to take a look at some advanced examples in integration by parts. Let's go and see the story of this topic. So, the examples I have for you are as indicated here. First one is integral of x cubed sine of 2x. We are going to solve this thing by something we call reduction. Reduction means what we are aiming for is reducing the power that you see from 3 to 2 to 1 to 0. And by the time we get to power 0, of course, this is going to be just sine of 2x, and the integral of that would be very easy. Another example that is a bit more advanced than the usual one are the so-called self-referral problems. Self-referral means the following. You start with an integration problem. You apply integration by parts. You go through several steps, and at some stage an integral appears that's just like what you had at the very beginning. So if you collect them to one side, at that point you can actually find the integral. One of the more famous examples here is this last one I have indicated, exponential of ax cosine of bx or exponential of ax sine of bx. This is more important than the rest of these because it's something that shows up in study of vibrations, either mechanical system or electrical system. This is very important there. Rest of these things, every now and then some of them show up in some physics problem, but let's go ahead and see what we do with the very first one. Probably in this lecture I just do this, and then we'll do these in separate lectures. Okay, let's remind ourselves what was the procedure. For integration by parts, we had to identify a u and a v. So we had this general formula, integral of u dv was u times v minus integral of v du. Okay, in this problem we are going to take u to be x cubed because its derivative is going to be smaller power, and then by that reduction of the power we hope that we achieve a sequence of integrals which are going to be easy to handle at the end. So let's go ahead and see how we are going to handle this. So I have the integral of x cubed sine of 2x dx. I want to process this thing, so I take u to be x cubed, and whatever is left is my dv. Now I take a derivative of this thing, so du therefore is going to become 3x squared dx, and then v is the antiderivative of sine of 2x. Okay, what is the antiderivative? Let's get everybody engaged a bit here. What is the antiderivative of sine of 2x? Okay, did you make your decision? Let's double check. So antiderivative of this thing is, if you just say cosine of 2x, of course derivative of cosine of 2x has a couple of things off from what we want. First of all, derivative of cosine is minus sine, so to compensate I need a minus. Second, by chain rule a factor of 2 is going to come out, and to avoid that we have to take this thing and divide by 2. So that is my v. Now this is easy. U times v, we put the minus sign up front so that there wouldn't be a confusion as to what we meant, not to be mistaken for a subtraction. So I write minus x cubed cosine of 2x over 2. So we put this minus up front. Then minus integral of v du. So v is minus cosine of 2x over 2. Let me put all of the v here, and du is, all of it is here, 3x squared dx. Let's separate this preparatory steps from what we have here. So all I get is minus x cubed cosine of 2x over 2. Let's put this 3 and a 2 and a minus in this minus, merge them all, put it outside, so we reduce the clutter a bit. Typically we put the polynomials first, x squared cosine of 2x, to avoid the confusion in reading the integral. Okay, now do we see why we call this method the reduction method? I started an integral I wanted to do here and had x cubed in it. At the very end I have still an integral, but the good thing is that now is a x squared in it. So that's a ray of hope, that's a light at the end of a tunnel essentially, that if we keep repeating this process, from 3 we went to 2, if we repeat again we go from 2 to 1, and then from 1 to 0, and out comes our final answer. Now it's going to be kind of repetitive, and there's room for errors. There are lots of numbers floating around, pluses and minuses and so on, so it's a bit challenging to get everything in place. So you need to write very clearly, and there would be a method that we are going to explain later on that tries to compress all of these things in one place and make it a bit easier, but that process has so many steps in it, however you want to approach it. Okay, so then we have to start doing this problem again. So the problem is again like those Russian doll situations, that you open one, then there is a smaller doll inside of that, and now you open that one, there's another doll inside of that, and so on, and you have to keep all pieces in the right place. So here let's go put this thing, x squared cosine of 2x dx. So we saw this thing works, we're just going to copy that. Of course now we are going to recycle our letters, and u and v are going to mean new things, unless you want to go ahead and use all sorts of new letters, and that's probably going to be as confusing as recycling it. So with that provision we go and say, okay, now u means x squared, and now dv means cosine of 2x, and of course du is going to be 2x dx, and the v is the antiderivative of this one. What's the antiderivative of cosine? Well, of course sine. No, sine of what? Sine of 2x. And then what? Is that it? Now of course I have to divide by 2, so that when you differentiate this thing, this 2 and that 2 cancel each other out. So u times v is going to be x squared sine of 2x over 2, and then minus v du, this times that is going to be sine of 2x divided by 2 times 2x dx. Let's separate these things, so let's simplify. Becomes x squared sine of 2x over 2. This 2 and that 2 cancel each other out, and now I have minus integral of x sine of x, excuse me, sine of 2x dx. Of course it's always going to be 2x here. So again, let's remind, we went from 3 to 2, we processed 2, 2 comes to 1, and of course you process that one more time and you are going to hit 0, and then you have your final answer. So let's do this one again. So, what would I have? I have integral of x sine of x, again sine of 2x dx. We are going to take u. We have done this problem, but just to repeat, u is x, du is of course just dx. If dv, I forgot to put my dx here, if my dv is now sine of 2x dx, then v as before is going to be minus, just as what we did here, minus cosine of 2x over 2. So product of these two, we put the minus up front so that doesn't look like subtraction, and then x cosine of 2x divided by 2, and then minus integral of the product of these two, which is going to be minus cosine of 2x over 2 times dx. So that simplifies to minus x cosine of 2x over 2. These two minuses cancel each other out. Antiderivative of cosine is sine, so I'll have sine of 2x now divided by, have to divide by another 2, becomes 4. In all of these stages, we don't bother writing with the constant. At the very end, we are going to add a constant to our final integral. So to avoid the clutter, we just didn't write all the constants in every one of these steps. So let's all of this thing on the side. Let's see what we have. So I have minus x cubed cosine of 2x over 2 plus 3/2 of 1 x squared cosine 2x, that is this. So I have to write 3/2 of, this is x squared sine of 2x over 2 minus this integral, which is that. So I write it. I have to subtract this. I'm going to subtract this expression, so I'm going to put it in a parentheses. So it's going to be nested parentheses minus x cosine of 2x over 2 plus sine of 2x over 4. Let's clean up. Minus x squared cosine of 2x over 2. 3/2 times this becomes 3x squared sine of 2x over 4. 3 minus minus and a half makes 3/4. Cosine of 2x. 3/2 minus times a quarter becomes minus 3/8 of sine of 2x. If you want to make it look a little bit perhaps cleaner, you can collect the cosines and collect the sines together. So if you want to do that, so I put the cosine in one place and then I put the sines in one other place. For cosine I have minus x squared over 2 from here. Excuse me, I have made a mistake. This has to be 3. So this is 3 and this is 3x over 4. Okay, this 3 is just copy of that 3 over there. For the sine, I have 3x squared over 4 here and minus 3/8 over here. So if that looks any better, that is the final answer for this problem. And let me ask you to do another one of these problems. Let's leave this one to you. Say x squared sine of say 6x. Okay, so again, what was the idea of the method of reduction? Typically a polynomial times some other function that we can integrate easily, and then by repeated use of integration by parts, the power of this polynomial goes down until it hits 0, at the very end we are going to have just some function related to this emerging. Now as we said, the algebra gets a bit crowded, and sometimes we are going to use some shortcuts to collect all of these steps in one place and make our problem a little bit more bearable. And in your textbook there is a method for doing this. It's called the Tabular Method. You want to study that, and here is a version of that. There's going to be handouts in my website that you can also read and then see how does this go. Okay, so here is an alternate way of handling such problems with a slight modification of the integration by part formula. First of all, I'm going to introduce some new notation. I'm going to have function up is going to mean antiderivative of that function. So integral of f. So for example, if I have x cubed up, it simply means x to the power of 4 over 4. Again, we dispense with the constant here. I forgot to put a constant in this problem too, some constant, just to avoid the clutter. Now, sometimes in the process that we went through, we saw that we have to repeat our actions. So sometimes we want to take antiderivative twice. What does that mean? It means antiderivative of the antiderivative. So if I have x to the power of 4, next one is going to be x to the power of 5, and there was a factor of 4 here. There's going to be another new factor of 5 here, so it becomes x to the power of 5 over 20. So that is the result of 2 rounds of anti-differentiating this. Comparable notation, f down, this simply is the derivative. Let's try again. If I have x cubed and I take it down, it simply means I'm taking derivative, so that's just obviously 3x squared. And then what if I want to do a repetition of this thing? Second round of this simply means differentiate the derivative. Of course, what's the derivative of 3x squared? Well, that's just 6x, and so on. So we are making this notation so that we can write the integration by part formula in a slightly different manner. So if you have f times g, product of two functions, and you want to integrate it, one way to do this thing is to pick one of these functions to take up, and you repeatedly do the following. So you, for example, here you up twice and take this one down once, and then if you want to continue, this one will be up 3 times and this one will be down twice, and so on. What do you think is going to be next? The signs alternate and the powers go up. So the next one will be, what would be here? So it's going to be 4, for example, and this one going to be down by 3, and so on. You keep doing this thing as many times as needed, and the signs are going to alternate. So down the road you are going to have either a plus or minus depending on odd or even number of steps you have taken, and then f going to be taken up by, say, n plus 1 steps. G is taken down by some, say, n steps, and out comes the last term. The last term is just going to be the last integral here. So the sign is going to flip one more time, so minus and plus perhaps, and inside the integral we are going to have f power n plus 1 or up n plus 1 and g down n plus 1. Okay, now the formula looks a bit crowded and complicated, but it's really very simple. So you have a product of two functions, you pick one of them to be taken up, so up once, twice, three times, and so on. Take the other one, start by itself, and then take it down once, twice, three times, and so on. At the very end, we still have one integral. One function is taken up to a certain level, the other one is taken down to the same number of levels, and the sign in front of these are alternating. So this is same as integration by part formula. It's repeated over and over again. Suppose we want to apply this to the problem that we have at hand. So let me write it. Say we had sine of 2x. Okay, so this number one function, call it f, and the other one, let's call it x cubed dx. Okay, which one are we going to take down? Well, if there's a polynomial, it's to advantage to take that one as our g function, to take it down, because eventually a polynomial, if you differentiate it often enough, it hits 0. And that's going to be a happy coincidence for us, because the last integral just gets wiped out. So here I'm going to identify f with sine, g with x cubed. So what am I supposed to do? I'm supposed to take first function. So I'm going to write what am I going to do, and next I'm going to do it next. So sine of 2x has to be taken up, which means I have to take the integral of it, antiderivative of it. I'll do that later. X cubed, I just leave it alone. Next, I'm going to alternate. Then this one, whatever I got in the previous stage, I'm going to do that one more round. So double up, if you wish to call it. And x cubed now starts going down. In the next step, I'm going to take whatever function I had here, taking it up twice. I'm going to take it up one more time, so it's going to be 3 times. This one is going to go down twice, and again flip the sign. It's going to be sine of 2x. Now this one 4 times, and then x cubed, this one 3 times. Now remember, if you take x cubed, differentiate it, you get x squared. Of course, some number, but this becomes x squared. Then it becomes x, then it becomes a number. If you do it one more round, you're going to hit 0. So it's good to put that last one inside the integral. So it's going to be sine of 2x. By now, this number is going to be same as that. It's still going to stay at 4. This one is going to be taken down 4 times, and the fourth derivative of x cubed will be 0, and that is a happy day for us, because we don't have to worry about that integral anymore. Now next we are going to write what's the antiderivative of sine of 2x. I hope I haven't lost you. What's the antiderivative of sine of 2x? What's that? So antiderivative of this is going to be, of course, minus cosine of 2x over 3. Okay, we leave that here, leave that one over there. Now I have to do a subtraction. Then whatever this thing is, I have to anti-differentiate this thing one more time. Another error of mine. That's it too. What's the antiderivative of this expression? Well, I have a 2 here. Another 2 is going to come because of the chain rule. So that becomes a 4. Cosine becomes sine, and the minus stays. Next, this has to be differentiated. That is easy. 3x squared plus. This has to be anti-differentiated again. So anti-differentiate that one. What do I get? 2 comes in the denominator, so it becomes 8. Antiderivative of sine is minus cosine, but this minus becomes plus cosine of 2x. And then derivative of 3x squared, that differentiation is the easier one, 6x. One more round. What's the antiderivative of this? Due to the chain rule, 2 goes in denominator, this becomes 16. Antiderivative of cosine is sine. Derivative of 6x becomes 6, thankfully, and then we hit the end. Antiderivative of 0, well, it's just a constant. Now time to clean up, so I write this thing minus x cubed over 2 cosine of x, 2x, minus 3 and 4 makes 3/4 of x squared sine of 2x, 6 over 8, that is 3/4 of x cosine of 2x, 6 over 16, same as 3/8 of sine of 2x, and a constant. Let's clean up. So if I collect my cosine, what do I have? Minus x cubed over 2 and 3/4 of x. If I collect my sines, let's keep our fingers crossed, make sure we are not making any mistake here. I have 3/4 of x squared minus 3/8 and a constant. So that is pretty much what we had here, hopefully. Okay, so for this, in your textbook you read something called Tabular Method. It's the same thing. In the text it's written as a column, vertical column. Here we have written it as just a line formula. They talk about the same thing. Okay, so of the problems that we wanted to do, we did an example of reduction. We also opened the topic of a tabular method or generalized integration by parts. Let's keep these other problems for the next round, and I invite you to try to do this one by yourself. It takes a few minutes, but you should be able to find the formula for that. And again, let me remind you, it's a very important problem in engineering because all vibration problems lead to that kind of an expression. Okay, until next time, good luck and God bless.